Hi class, welcome back. Today's lesson is on magnetic flux. This is class by Raj teaching for Physics Semester 2 STPM. The learning outcome for today's lesson is to define the magnetic flux.
This lesson, let's turn on to our textbook, Oxford FAJAR, page 197. Today we are going to look at a new chapter which is an electromagnetic induction, and in order to do that we have to understand another quantity which is a magnetic flux. Magnetic flux is not a new quantity, okay? Maybe it is new in the magnetic field, but you have come across flux in electric. Where in chapter 1 you have come across the word as electric flux. That was electric flux, that means in the definition of the electric field, but here is magnetic flux in the definition of magnetic field. Okay, alright, so qualitatively magnetic flux we can put symbol is 5. Okay, so the book says here qualitatively means doesn't have data included in it, so it's just a simple way of explaining. Qualitatively, the magnetic flux through an area represent the number of magnetic line of forces that pass through the area. Okay, and then what does it mean? Magnetic flux through an area represent the number of magnetic line of forces that pass through the area. That is qualitatively. But quantitatively means we include the data, okay, or we include the quantity that has to be observed. Okay, the magnetic flux through an area which is normal to the magnetic field is B, is given by phi equals to B dot A. Okay, so that is how they define. This is the definition of magnetic flux. Okay, let's look at this diagram here, class. Okay, magnetic flux. Okay, magnetic flux. What does magnetic flux is defined? Magnetic flux. Now, what is now magnetic flux? Qualitatively, we can describe it in two ways. One is by qualitatively. Okay, qualitatively. Another one is by quantitatively. Quantitatively. Okay. Now, by qualitatively, it says number of magnetic line of forces that pass through the area. Number of magnetic line of forces. Magnetic lines of forces that passes through an area. That pass through an area. Okay. And quantitatively, it says magnetic flux through an area which is normal to the magnetic field, where they say it is phi equals to B dot A. Okay, let's look at this example, class. Alright, let's look at this example here. Now, this is the first example. This example is the first example. Okay, I have a area here. Okay, so magnetic field line of forces with a strength of B is passing through the area. Okay, so the direction of the magnetic field line of forces is in this direction. Okay, alright, so magnetic flux is the B, the magnetic field line of forces that pass through an area. Now, this area is the area, okay, if I take another color pen, okay, the area direction will also be in this direction. That means is the surface area direction. Okay, in this direction, which is A. Okay, so that's why it says quantitatively, magnetic flux through an area which is normal. Okay, which is normal, where B and A are normal. Okay, to the magnetic field. So B phi equals to B times A. Okay, again, if you look at this picture, the B is in this direction. Okay, and the surface area is also facing in this direction. So if I want to highlight the surface area, it is facing also in this direction. So magnetic flux is through an area is normal to the magnetic field. So it's normal to the magnetic field. So phi is equals to B times A. Okay, phi is equals to B times A. This is the definition of magnetic flux. Okay, now let's look at another example. If we tilt the surface area this side, so the surface area is in this direction. Okay, surface area is in this direction. Okay, and then if I draw an arrow, a line, it will be like this. Correct? Okay, so this is surface area. Then the B, if you see the B is in this direction. Okay, the B is in this direction. Okay, so the magnetic flux is equals to the B, which is normal, times with A. A is in this direction. So if you have an angle theta here, so the A that is normal to the B will be A cos theta. Correct? So B equals to, phi equals to B times A cos theta. Okay, so you get B A cos theta. Phi. Alright, so this is the definition of magnetic flux. Now, what is the unit of magnetic flux? Okay, unit of magnetic flux. The unit of magnetic flux is called as Weber, which is capital W and a small b. Okay, alright. Now, I want to let you all see one word. Okay, I want to explain to you all this sentence here. Okay, where the direction of the area vector A is perpendicular to the area A. Okay, now what does that mean, class? Okay, let's look at this. Why the book says so? Where the direction of the area vector A is perpendicular to the area A. Okay, direction of the area vector A. That means area in vector. Okay, area that is associated magnitude plus direction. If you talk about area, you associate it in magnitude and direction. Okay, is perpendicular to the area. Okay, is perpendicular to the area is talking about area which is magnitude. Now, why is it here they said normal and then here they said the word perpendicular? Okay, here when they say the word normal, they are actually talking about the between the A and the B. Normal A and B. Okay, but here when they talk about area vector A is perpendicular to the area A, they are talking about area A, which is a vector perpendicular to the area A of magnitude. Okay, like say for example, if I take this, yeah. Okay, now if you are supposed to find the area, you are supposed to find the area of this. How do you find? Okay, so this is the surface. Okay, this is the surface. Okay, so you want to find the area. So this is the radius. So the area will be pi r square. So when you talk about area is pi r square, you're talking about area which is a scalar. Area which is a scalar where you only take note of its magnitude. Okay, alright. But when you are talking area in associate magnitude plus direction, okay, which I'm going to draw with the yellow one. So the magnitude is pi r square, but it's facing in this direction. The surface area is facing in this direction. So we call this area vector A. Okay, we call this area vector A. Okay, this one we call as area, because you take the area in this direction with in respect to pi r, correct? This one is area, but area vector A. So it's magnitude plus direction. So they are perpendicular. Okay, that's why the book says the word where direction of the area vector A is perpendicular to the area A. That means they are talking about this area, which is in associate together with the direction, is perpendicular to the area which is the scalar, which is the magnitude. Okay, is area a vector or a scalar? Then there's a question arise. Okay, now from form 4 to form 5, you always study that area is actually a scalar. Okay, area can be a scalar if only magnitude is talked about. Okay, area will be a vector if you have the magnitude and also the direction. Like when you see, when the book mentioned here the definition, through an area which is normal, that means it's talking about vector area, which is area in magnitude with direction. Okay, so let me make clear that to you. Alright, okay. Okay, so come, let's go to the next one. Alright, so this is A, this is for this, and this is for this. Alright, so the unit for magnetic flux is Weber. Okay, is Weber. Alright, now figure 17.2a shows the plane of a coil with N turns. Okay, now let's look at the word N turns. We have coils of N turns. Here we have only one coil. Here we have coils with many turns. Okay, which is N turns. So how do we want to find the magnetic flux? Okay, magnetic flux for one coil. Magnetic flux for one coil will be phi is BA for one coil. Okay, but if the coil got many coils, then the total magnetic flux for the whole coil, the number of coil, we call it as magnetic flux linkage. Magnetic flux linkage. Okay, for one coil is phi equals to BA. For many coils, okay, we call it as magnetic flux linkage. So usually magnetic flux linkage are used for coils and solenoid because there are so many number of turns. Okay, so magnetic flux linkage is equals to number of turns times with magnetic flux of one coil. Okay, magnetic flux. So therefore we have N is phi equals to NBA. Okay, so you have to know this formula. Alright, okay, so in this case we know the B is in this direction. Okay, the B is in this direction. Wait, I take another pen. B is in this direction. Okay, and then the A is also in the direction. So A and B are normal to each other. Okay, alright, so we get the phi equals to BA, and then we find the magnetic flux linkage. Okay, now what about this kind of question where you have the number of turns of coils, okay, but it's tilted with an angle of theta from the normal. This is normal, right? Now the coil is tilted with an angle of theta. Okay, so how do we solve this? Okay, first we find the area. Okay, the vector area. The vector area is in this direction. Okay, and the magnetic field is in this direction. Okay, so you realize there's an angle of theta between the area and between the magnetic field. So there's an angle of theta. So phi, okay, why we take cos theta? Because it's A cos theta is the one that is normal to the area, normal to the B. A cos theta is the one that is normal to the B, because the B is in this direction. A cos theta is normal. Okay, so phi is equals to B A, where B is times with A cos theta. Okay, so B A cos theta for one turn. For one turn. But this one got n turns. So how do we going to solve this? So magnetic flux linkage. Okay, magnetic flux linkage is equals to the number of turn times with magnetic flux. Then you will get the formula NBA cos theta. Okay, NBA cos theta. Okay, alright, now let's look at the book. The book says figure 17.2 shows the plane of a coil with n turns. Plane of a coil with n turn, each of area A normal to the magnetic field B. Now what does this sentence mean? Area A normal to the magnetic field B. That means area A is area vector A, yeah, is in this direction. Okay, and then B is also in this direction, so they are normal to each other. Okay, the magnetic flux to each turn, okay, the magnetic flux to each turn of the coil is BA. That means it's trying to say phi equals to BA. Magnetic flux is equals to BA. The magnetic flux linked with the coil, the magnetic flux linked with the coil is called as magnetic flux linkage. Okay, magnetic flux linked with the coil is called as what? Magnetic flux linkage, where I put L as the word from linkage, magnetic flux linkage. Okay, so phi magnetic flux linkage equals to N times magnetic flux, so you get NBA. Okay, if you realize that the book doesn't put phi L, okay, it's okay, but most of the time they will mention with the word is magnetic flux linkage. Okay, so you have to be careful when you do the question, is it magnetic flux or is it magnetic flux linkage? If it is a solenoid, it has to be magnetic flux linkage, because solenoid got number of turns, a lot of n, and same goes to coil. Okay, all right, if the normal to the coil makes an angle theta, if normal to the coil makes an angle theta with the magnetic field, that means the B is in this direction, the A is in this direction, so the angle is theta. So magnetic flux linkage will be NBA cos theta. Okay, NBA cos theta. Now what is magnetic flux? The number of magnetic field lines that pass through the area. Number of magnetic field line of force that pass through the area. That is explained by qualitatively. Okay, right, so you get here the answer NBA cos theta. In case, okay, we have a coil is wound on a piece of material of relative permeability of mu r. That means this is the coil. Okay, lot of number of turns. Okay, lot of number of turns, and then it's wound piece of material like this. Then the magnetic flux linkage phi L, okay, is mu r times with NBA. Okay, n is because of number of turns.